in the previous slide, we talked about different elements of reinforcement learning through the example of the trash picking robot. Now we'll see some of the different or basic approaches for doing RL, and one of the first one which we are going to talk about is called the multi-armed bandit. Now the name multi-armed bandit comes from the slot machines which you find in casinos. These are your slot machines which has got different levers, and you pull those levers, one of these levers, and then you get some reward, either a jackpot or maybe some rewards which you will get. So the multi-armed bandit, the name comes from different levers which you have to pull for that particular slot machine. And one of the important thing which you have to which you note here is called the dilemma between pure explorations and exploitation. Let's understand what this is. Now, based on your experience in pulling different levers, you pulled from lever 1 to lever 5. Say the multi-arm bandit has got 10 levers. Let's say for example 10 levers, and then you start pulling from first to fifth lever, or you start playing only the first 5 levers. Now, after a certain amount of interactions or a certain amount of plays, you find that the third lever is consistently giving you better reward. So what you do, you try to use third lever more and more so that you kind of maximize the rewards which you get. And this is called exploitation. That is, you're exploiting your knowledge that the third lever is going to give you more rewards, and then you try to use that more and more. Now, that's a good strategy. So you understood that third lever gives you so much of rewards, and you keep on exploiting that. But is that good enough for from a long-term perspective? Does it guarantee you that you get the best reward possible? Maybe not, because you have tried only from the first lever to the fifth lever. There are still 5 more levers which you have not explored yet. What if one of these levers gives you a much better reward? So you won't find out unless you explore that. So this is what is meant by exploration. So usually this exploitation versus exploration dilemma is when you try to exploit the lever or the arm which gives you the better results, and in the same way, on a case by case basis, you try to explore other arms also. And this is called a psi greedy method. Psi is a parameter which gives you a probability in terms of whether you need to explore or exploit. Let's say, for example, psi value is just says 0.1. Now you just randomly take a random probability number between 0 and random probability number. Say if the random probability number is more than this psi, that is 0.1, you exploit the reward or the arm which gives the best reward. And if it is less than psi, you kind of explore different, randomly pick an arm, any of this arm, you do an exploration. So this is called a psi greedy method, and there are different methods in terms of solving a typical bandit problems and finding the best reward possible. So at the end of the day, what you need to find is what arm to pull. Are you finding out what arm to pull on a long-term basis? And that is the ultimate aim of a multi-armed bandit. Now we'll get into the context of how this could be used from a reinforcement or a recommendation system perspective in the subsequent slide, but let's try to understand what a multi-armed bandit is. Now we will talk about another approach for reinforcement learning called the Markov decision process. We'll get into that in the next slide. Markov decision process is another approach which is widely used for solving reinforcement learning problems, and Markov decision processes can be implemented using a technique called dynamic programming. Let's try to understand this Markov decision process from the context of the robot or the trash picking robot we saw earlier. Now, Markov decision process assumes the knowledge about the environment or it's called a model-based approach. Now, what is this model-based approach? So in a model-based approach, you very well know what are the states which you're going to get into, what are the actions to be taken, and there is something called a transition probability. That is, at what probability do you move from a certain state to another state? By taking some actions, at what probability do you get into the different states? Let's try to understand from these model-based approaches or these transition probabilities, etc., from the context of this of the trash picking robot. Now let's look at the state in which, let's look at a state, the state of high charge, which is here in the left. Now, from the state of high charge, we know that the robot can take different actions. One is it can wait, keep on waiting in the high waiting when it is in the high charge, or it can start searching also. Now let's look at what is this transition probabilities. Now, if the robot was in a state of high charge and it starts or it's waiting there, then by a probability 1, it will still remain in a state of high charge, because you know that you are not searching at all, and you're just waiting there. You still continue in a state of high charge. Now, let's say the robot is in a high charge and it takes an action to search. So in a search, when it does search, it can either be continue to remain in high charge, or it can go to a low charge. Now let's say there is another probability value, that is, say, alpha. It could be any value, say for example 0.2. So let's say alpha value is 0.2. So by a probability of 0.2, when it starts searching, it continues to remain in its high charge, but by a probability of 0.8, that is 1 minus alpha, it goes into a low charge. And similarly, so that's the concept of these transition probability. And similarly, you have transition probabilities in each of the states, and based on each of the actions which it takes, and what is the probability of getting into the next transition state by taking the actions. That is what these transition probabilities are. So in a model-based approaches, you very well know which are the states, what are those actions which you need to take, and what are the transition probabilities through which you will get into the other state based on the actions which you take from a current state. Now, in a typical Markov decision process, one of the basic premises, and you might take different actions and different states you will get, and different rewards you will get in the process. But all what matters in a Markov decision process is the last step which has been taken. So your next step is dependent on the last step which has been taken. So that is the basic premise of a Markov decision process. Now, having understood Markov decision process, we'll try to understand other different types of reinforcement learning problems, like your temporal learning or Monte Carlo approaches.